Hello. In this lecture, we are going to look at the situation of oscillations. And we're going to look at the idea of what is called harmonic motion, which is basically repetitive oscillations about a particular point. On the screen, you see three examples of harmonic motion, circular motion, linear oscillations, and then this square motion. And all of them are oscillations about a particular point. All of them represent harmonic motion. And we're going to discuss some of the physics behind that in this lecture, and we're going to look at a very specific example of simple harmonic motion. And that is the mass spring system. We can imagine an ideal spring hooked up to a mass that is placed on a horizontal surface. We stretch out the spring, we release the mass from rest, and it starts oscillating back and forth. And in principle, this oscillation would last forever. If there's no friction, if there are no other types of energy dissipating the kinetic energy from the system, no types of work dissipating kinetic energy from the system, this motion goes on forever. We're not going to be looking at more realistic situations in which we have dissipative effects. That's a little bit beyond the scope of this course, but we can at least look at this ideal situation as kind of the zeroth order situation to gain a better understanding. Simple harmonic motion is a very particular type of harmonic motion. Technically, it means that the force that is trying to pull the object back to its equilibrium position, where the net force is zero. Simple harmonic motion is when that restoring force is proportional to the object's distance from its equilibrium point. So remember the mass spring system and Hooke's law. Hooke's law says that the magnitude of the spring force goes as a spring constant times x, where x is the distance of the object from its equilibrium position. That is an example that gives rise to very particularly simple harmonic motion. And in simple harmonic motion, we can use sine and cosine functions to describe the motion. In order to understand how we're going to describe the motion, take a look on the screen. What you see up top is an object oscillating in one dimension back and forth, left to right. And underneath it, you see a graph of displacement versus time. And along with it, you see a moving little circle. Now, that moving little circle, its location along the vertical axis, which is displacement, is representative of the displacement of the actual oscillating square. Notice that when the square is farthest to the right, the little circle is at the highest point of its motion at a displacement of capital A. When the square is farthest to the left, the little circle is at its most negative displacement, namely at negative A. And when the little circle passes through zero, that means that it's passing through a displacement of zero. That's when the object is in its equilibrium position. When we look at equations that describe displacement as a function of time, we're going to imagine it as displacement on the vertical axis and time on the horizontal axis. But this is still representing one-dimensional motion. Please don't be confused by the fact that you see horizontal and vertical axes. It's really one-dimensional spatial motion. I'm also going to point out a little bit of terminology. I use the symbol capital A to represent the maximum displacement of the object from equilibrium, and the word for that is amplitude. Amplitude is the maximum displacement, the farthest the object gets from its equilibrium position. In our mass spring system, since it's purely horizontal, we don't have to worry about gravitational potential energy. but it is moving, so we have to worry about kinetic energy. And there is a spring involved, so we have to worry about elastic potential energy. So at any given instant, we can say that the total energy is kinetic energy plus potential energy, 1/2 mv squared plus 1/2 kx squared. And the thing is, without any friction or anything else bleeding energy away from the system, this sum at any given moment will equal the same value. It will equal the total energy of the system. When the object is at its maximum possible displacement, if you'll remember from the animation on the previous screen, for instance, when the object approaches the rightmost point, it's moving to the right initially, and then immediately afterwards it's moving to the left. That means that there was a moment where the object was not moving. First it had positive velocity to the right, then it had negative velocity to the left. In order for there to be a smooth transition from a positive value to a negative value, there is an instant where the velocity is 0. And that occurs at the maximum possible displacement. That occurs at the amplitude. So, for instance, when the object is at the amplitude, at that instant, its speed is 0. And its total energy is equal to 1/2 times k times the square of the amplitude. On the other hand, when the object passes through its equilibrium position, x is 0. X might be positive, x might be negative, but when the object passes through the equilibrium position, x must be 0. On the other hand, that's the instant the object is moving fastest. If the displacement from equilibrium is 0, if x is 0, then all of the energy is in the form of kinetic energy. The object has its fastest speed, v max, and we can say that the total energy equals 1/2 v max squared. So we have these three expressions for the total energy. 1/2 k times the square of the amplitude, 1/2 m times the maximum speed squared, and then the most general situation, 1/2 mv squared plus 1/2 kx squared. At any given instant, all of those should yield values that are equal to each other, equal to the total energy of the system, which is conserved. Let's put this into an example. We have a 293-gram mass. It is oscillating horizontally at the end of an ideal spring, and the spring has a spring constant of 19.3 newtons per meter. We're told that the amplitude of the oscillations is 17.3 centimeters. What is the speed of the mass when it passes through the equilibrium position? Now, the most annoying part of this problem, I hope, is simply the fact that we need to convert to standard units. The mass is given in grams. We need it in kilograms. We have to move that decimal point over 3 places. 293 grams is equivalent to 0.293 kilograms. And for the amplitude of 17.3 centimeters, we have to convert that to meters. We move the decimal point over 2 places, and the amplitude in standard units is 0.173 meters. The maximum displacement is the amplitude. A and 1/2 Ka squared, as we discussed earlier, is the total energy of the system. We know K, we know A, we plug it in. We get that the total energy of the system is 0.2888 joules. This system has the same total energy as the object passes through equilibrium. But as the object passes through equilibrium, there is no elastic potential energy. All of the energy is kinetic. The object is moving its fastest. So we can take that 0.2888 joules and say, well, that's the maximum kinetic energy, and we can solve for V max. V max is equal to the square root of 2E over m. Now we know E, the total energy, and we were given m, and we converted that to kilograms. We plug in the numbers, and we get that the maximum speed is 1.40 meters per second. So these are very ordinary numbers in real life. So you wouldn't expect a spring to cause a mass to oscillate at hundreds of meters per second, nor would you expect it to oscillate at a speed of, 100th of a millimeter per second. The fact that it's 1 or 2 meters per second is really not that unreasonable. We are going to make we're going to skip some calculations. It is possible to derive the equation that you see on the screen, that the maximum speed is equal to the square root of k over m, and then that result times the amplitude a. If we know k, and if we know m, and if we know the amplitude a, then we have enough information to be able to calculate the displacement and the velocity and the acceleration of the mass at any instant in time. The calculation of the acceleration isn't so bad, because remember that the acceleration is proportional to the force, and in this problem, the only force that's causing motion is the spring force. We can use spring's force on Hooke's law. A more formal rendering of Hooke's law is that F equals minus kx. Now this minus becomes important, because the minus is giving us information about direction. If x is to the right, that means x is positive, but it means that the force is trying to pull the mass back to the left, because equilibrium is to the left of the mass if the displacement is positive. On the other side, if the mass is pushed to the left, then the spring force is going to push it to the right. So the direction of the force acting on the mass is always exactly opposite in direction to the displacement of the mass, and that's a consequence of Hooke's law. But it also means that the acceleration, which is ma, must also be equal to minus kx. And that allows us to say that the acceleration is simply equal to minus k over m times x. So if we know x, and if we know k and m, we can find the acceleration a pretty quickly. Now take a look at the plot on this screen. It's a plot of displacement versus time. And I want you to consider the instant in time denoted by point P. And I want you to visualize what must be happening to the mass. Is it speeding up or slowing down? What can we say about whether the acceleration is positive or negative, whether the velocity is positive or negative? Stare at that. Ask yourself, as we progress through time and we are at point P, what must be the sign of the velocity? What must be the sign of the acceleration? As always, if you're not sure of your answer, ask questions at the start of class. Let's ask the following question based on the spring mass system that we had earlier. So the amplitude of the motion is 0.173 meters, the mass is 0.293 kilograms. I should read kilograms, not meters. The spring constant is 19.3 newtons per meter. What are the magnitudes of the displacement, velocity, and acceleration when the mass is 3/4 of the way from equilibrium towards the amplitude? Well, what do we mean by 3/4 of the way from equilibrium towards the amplitude? And that means that we're 3/4 of the amplitude. The displacement is 3/4 of the amplitude. 3/4 of 0.173, 0.75 times 0.173 is 0.12975 meters. So we have the displacement. We also have k and m. So that allows me to find the magnitude of the acceleration pretty quickly. If we're looking for the magnitude, we don't worry about the minus sign. K is 19.3, m is 0.293, k over m times our displacement, and we get that the acceleration has a magnitude of 8.55 meters per second squared. The velocity takes a little bit more effort to find, well, the speed to be exact, since we're looking for the magnitude of the velocity. we can say that the total energy is equal to 1/2 mv squared plus 1/2 kx squared. And the only unknown there is going to be V. Because remember, we found the energy earlier. We found the energy to be 0.2888 joules. So if I take that general expression for the energy, the sum of kinetic plus the sum of potential, then V must be equal to the square root of 2E minus kx squared all over m. I know E, I know K, I know X, I know M. We plug it in, and we get that the speed is 0.929 meters per second. Now, while I'm thinking about this, I'm going to fix that because that is supposed to be kilograms. And that means that I'm going to have to fix the rest of this problem too, but you get the idea. I will fix it. Oops. Now, in oscillatory motion, in simple harmonic motion, we have two very closely related quantities called the period and the frequency. The period is the time for one full oscillation. But be careful, one full oscillation, if I start at positive A, one full oscillation goes from positive A all the way to negative A and then back to positive A. That's a full oscillation, and the time it takes for the object to go through that full oscillation is called the period. Period has units of seconds, although sometimes it's thought of as seconds per oscillation. Frequency is the inverse of period. Period is the number of seconds per oscillation. Frequency is the number of oscillations per second. So the number of oscillations we get in 1 second is the frequency. And while the standard unit of frequency is 1/seconds, or the inverse second, that quantity has been renamed in honor of a German experimentalist of the late 19th century. It's been renamed the Hertz. And the symbol is abbreviated as capital H subscript Z. Period is usually denoted by a capital T. Frequency is most frequently denoted by a lowercase f. But I have seen some texts in which frequency is denoted by a lowercase Greek letter nu, N-U, nu as in Nancy, nu. It's not a V, it's not a script V, it's the lowercase Greek letter nu. The actual relationship between frequency and period, well, they're inverses of each other. I can say frequency equals 1 divided by the period. I can say period equals 1 divided by the frequency. It's all good. We're going to draw up a comparison between this simple harmonic motion like you see on the right-hand side and circular motion. We have circular motion. Specifically, we spent a fair bit of time on uniform circular motion, namely motion in which the object goes around the circle at constant speed. We can see on the screen that the circular motion on the left, if we just look at the vertical location of the little object going around the circular path, we see that the little object on the right, the vertical location, is represented by its vertical oscillations. So we see that even qualitatively, there's definitely some similarity between circular motion and simple harmonic motion. And because of that, we introduce a concept that in circular motion is called angular velocity. The radians per second, how fast, it's a measure of how fast the object is going around a circle. It's going to be in units of radians per second, but conceptually you can think of it as degrees per second as to how rapidly the angle is changing over time. But we are going to have to be very specific about using units of radians at this point in time. Consider what happens if we release a mass in a mass spring system, we pull it out a distance a from equilibrium, we make sure it's at rest, and we release it. The mass starts off at an initial displacement that is at a maximum. It starts off with a velocity that is initially 0. And the acceleration is also at a maximum, but it happens to be at a maximum opposite in sign to the displacement, as we discussed earlier. Remember, in the mass spring system, that the acceleration equals minus k over m times the displacement x. In this situation, the motion that we get as a function of time is, as we say, sinusoidal. But we're using the term sinusoidal rather generally, meaning sine or cosine. What we specifically have here, though, is an object with a displacement starting at a maximum. And if I have a sinusoidal function that starts at a maximum, I have cosine. Cosine starts at a maximum. The cosine of 0 is 1, which is the maximum possible value. So as a general rule, I can express my displacement as a function of time as the amplitude times the cosine of omega times t. Omega, when we put it into this context, is the angular frequency, but it is mathematically very similar, conceptually very similar to angular velocity, so we use the same unit. But I can describe the location x, the displacement x, as amplitude times the cosine of omega t. I am able to describe the velocity as a function of time as minus omega times a times the sine of omega t. And I am able to express the acceleration as minus omega squared times a times the cosine of omega t, keeping in mind that omega squared, the angular frequency, is equal to k over m. Now, a little word about that velocity equation. We are releasing this mass from rest. The velocity behaves sinusoidally, but its initial value is 0. The sinusoidal function that has an initial value of 0 is sine. So we can represent the velocity as a sine function. And we would say minus omega times a times the sine of omega t. Now, there are mathematical derivations of these formulas. You don't have to worry about those derivations because it involves calculus. But hopefully you can accept and believe that these formulas are representative of the motion of a mass that is released from rest and oscillates in simple harmonic motion. There is a relationship between that angular frequency, omega, and regular frequency. And this is really one of the great annoyances in simple harmonic motion. There is the quantity angular frequency, and there is the quantity frequency. And they are not the same, although they are closely related to each other. How are they related? Angular frequency is radians per second. Frequency is oscillations per second. But one full oscillation is equivalent to 2 pi radians. So we have a factor of 2 pi between omega, the angular frequency, and f, the frequency. Omega equals 2 pi f. I can also bring in that relationship with the period, and I can also say that omega is equal to 2 pi divided by the period. So in the case of the mass spring system, if I know k and if I know m, I can figure out the period. I can figure out the frequency. Think about this question, another conceptual question. We have a block on a frictionless table, and it's going to be basically in a mass spring system, and it can oscillate back and forth without losing any energy. We pull it a distance d from rest, we release it, and it starts oscillating back and forth. But now let's suppose instead of pulling it a distance d, we pull it a distance 2d and release it from rest. What can we say about the amount of time it takes for the block to go from the initial location to the point where it's passing through equilibrium? As the block oscillates back and forth, it passes through the equilibrium position. So that means when I release it from rest, a short time later, it is at the equilibrium position as it's moving towards the other side. We release it a distance d, and we time how long it takes before the instant it reaches equilibrium position. We release the block from 2d, we time how long it takes for it to reach the equilibrium position, and we compare those times. What can we say about those times? When the distance pulled is 2d, is that new time twice as long as the first time? Is it the square root of 2 times as long as the first time? Is it the same? Is it the square root of 2 times less? Or is it a factor of 2 less? Think about it. Ask questions as necessary. Let's look at an example in which we describe the equations of motion for displacement and velocity and acceleration for this situation, a 1.52 kilogram mass attached to a spring with a spring constant of 24.9 newtons per meter, and it's pulled a distance of 9.15 centimeters from equilibrium and released from rest. What do we have? The amplitude is given, 9.15 centimeters. We're going to convert that to meters, 0.0915 meters. We have K and M. The angular frequency, omega, is the square root of K over M. The angular frequency is 4.047 radians per second. Omega equals 4.047. The maximum speed is omega times A. You saw that when we looked at the general expression for velocity as a function of time, minus omega times A times the sine of omega t. Sine never gets larger than 1. So omega times A times sine never gets larger than omega times A. The maximum speed is omega times A, and omega is 4.047, and A is 0.0915 meters, and so the maximum speed of this object is 0.370 meters per second. The acceleration is not constant. It's equal to omega squared times x. The maximum acceleration equals omega squared times the maximum displacement, but the maximum displacement is the amplitude A. So the maximum acceleration is equal to omega squared times the amplitude, 4.047 squared times 0.0915. We get that the maximum acceleration is 1.50 meters per second squared. And now that we know omega and the amplitude and the maximum speed and the maximum acceleration, we have our equations. The displacement as a function of time, 0.0915 times the cosine of 4.047 t. That's A times the cosine of omega t. The velocity as a function of time, minus 0.370 times the sine of 4.047 t. That's minus omega times A times the sine of omega t. The acceleration as a function of time, minus 1.50 cosine 4.047 t. Well, that's minus omega squared times capital A, the amplitude, times the cosine of omega t. So now for any value of time, I could tell you the displacement, the velocity, the acceleration. The one warning, make sure your calculator is in units of radians. It is vital in this circumstance. If you had to calculate the displacement at 5.3 seconds, well, t equals 5.3, 4.047 times 5.3. You have to do the cosine of that number. You have to make sure your calculator is in radians mode. If the object isn't released from rest, then if I wanted to account for that in my equations, I would need to introduce a quantity called the phase shift. And the equations become a little bit more of a pain to figure out. And by a little bit, I mean a lot of little bit. And I want you to be aware that we are capable of doing this. If the mass isn't released from rest, yes, we can accommodate for that. But I'm not going to worry too much about it. I want you to know it's possible, but really, that's all I have to say about that. You should be aware of the equations when the mass is released from rest. Don't worry about the situation where the oscillating mass is not released from rest. Okay, that's it. Bye-bye.